Good day to you all. We will be presenting our thesis entitled Significant Correlates of COVID-19 Risks in the Philippines using Spatial Modeling and Mapping. I'm Timothy Olvina, together with my research colleagues Shirl Ocampo, Pauline Roca, and Jasper Miranda. We are from STEM 12G in Dela University, Integrated School, Manila. Our research advisors are Professor Shirley Ocampo and Professor Regina Tresvalles. Our presentation is divided into 5 sections as visualized in the outline on your screen. To begin, the introduction. Originating from Wuhan City in the Hubei province of China, COVID-19 has had devastating effects on the Philippine community ever since its first entry into the country in January of 2020. As of June 12, 2022, the total number of reported cases in the Philippines has reached 3.69 million cases and 60,041 deaths. The ongoing pandemic has already severely affected the Philippine economy, healthcare, society, and Filipino lives. As past precedents have shown, with the Delta and Omicron surges, COVID-19 may strike at any time, and the Philippines is yet again preparing for a possible resurgence of COVID-19 in the days to come as a result of more variants. Let's move forward to the objectives. Ms. Ocampo.
To the research objectives, the first objective is to determine the significant COVID-19 correlates in the Philippines. This objective, or rather this research, is dependent on the availability of secondary data on government agencies like DOH. The second objective is to apply regression and spatial models to identify significant COVID-19 correlates. Note that this research integrates spatial components in modeling. Thus, applying spatial models is appropriate if there is spatial autocorrelation in the COVID-19 data across spatial units based on the computed Moran's I statistic. Third is to generate spatial and cluster maps of standardized incidence ratios or COVID-19 relative risk using the GeoDa software. It is important to remember that the maps created contain relative risk of provincial spatial units and cities in the national capital region. Finally, the last objective is to identify which provinces can be considered COVID-19 high-risk spatial areas, which involves observation of clustering in spatial maps. The floor is yours, Ms. De La Roca.
To our significance, this research is in line with SDG 3 on health and well-being. By determining the significant factors of COVID-19 cases, more reliable healthcare systems and protocols can be established. The research can also help the local government implement better policies by showcasing high-risk areas to COVID-19. This is done using data visualization via spatial maps. As such, identified high-risk areas can inform policymakers in setting priorities in health and COVID-19 mitigation policies. By doing so, the research findings bring new knowledge regarding the COVID-19 in the Philippines. In particular, the research included more factors of COVID-19 cases and relative risks, namely disease-related, population-related, environment-related, and health-related.
To our methodology. First, let's discuss the research activities. Throughout the research process, the group has accomplished the following. First, the group reviewed existing literature on COVID-19, statistical analysis, and spatial mapping to evaluate the research gaps. Second, 2021 COVID-19 data were collected from governmental agencies and cleaned using Microsoft Excel and Statistica. Third, the standard incidence ratio at the provincial level or city level for NCR was computed. Fourth, spatial mapping aids in visualizing high-risk spatial provinces in the country. Fifth, Moran's I statistic for determining the spatial dependencies in the data along with cluster maps. Lastly, multilinear and spatial autoregressive models were performed.
Secondary data was mainly obtained from the Department of Health as well as PAG-ASA, DENR, PSA, and FHSIS. So these are the variables used in the study, which are all per province or NCR city. As we can see, the criterion variables are COVID-19 cases, SIR of COVID-19 cases, and natural logarithmic function of SIR. These are the predictors, which include healthcare-related, population-related, disease-related, environment-related, and provinces. Regarding data analysis, 2021 COVID-19 statistics were investigated. Standard incidence ratio or SIR was used to measure a province's relative risk to COVID-19. Here is the formula for computing the provincial relative risk. To calculate the relative risk, common risk denoted by R was computed at the national level, as well as the expected count of COVID-19 cases denoted by E sub I. The SIR value determines whether the COVID-19 cases are within the anticipated range, meaning that the actual number of COVID-19 cases equals the projected number of COVID-19 cases, or if low risk, the actual number is fewer than the projected, or if high risk, it exceeds the expected number of COVID-19 cases. Ms. De La Roca, please continue the discussion.
Moving on with spatial mapping. Spatial mapping was used to visualize data and to investigate the clustering of COVID-19. Using GEODA, a standardized incidence ratio of COVID-19 cases was integrated in the Philippine map on a provincial scale with cities in NCR. High-risk provinces were shaded in dark colors, and light colors for low-risk provinces. Furthermore, the Moran's eye was used to measure the overall spatial autocorrelation and spatial dependencies among the spatial units. Shown on screen is the formula for computing Moran's eye. A positive spatial autocorrelation pertains to a more spatially clustered distribution, while a negative spatial autocorrelation means a more spatially dispersed distribution of the COVID-19 cases or deaths among the provinces. Additionally, cluster maps of the COVID-19 risk are also formed. Principal component analysis, or PCA, was conducted to avoid multicollinearity or redundancy in the set of predictors. Using Statistica, PCA basically converts a set of correlated predictors into a small set of uncorrelated predictors.
The multiple linear regression model, or MLRM, was used to determine the significant variables. The dependent variable is the natural logarithm of the computed SAR value, and the equation is displayed on the screen. Moreover, the MLRM's assumptions were satisfied explicitly, normality, homozygosity, and independence of the residuals.
After computing Moran's eye statistic, Spatial Autoregressive Model, or SAR, was used to also identify significant COVID-19 correlates, but takes into account spatial dependencies. Shown on the screen is the SAR model, having an optimal smoothing constant denoted by alpha of 0.5 and a spatial weighting matrix denoted by D, which has weights denoted by W sub ij, which if spatial units are in the same region, W sub ij is equal to 1, and if not, 0.
To start with the research and discussion, we have spatial mapping. Using GEODA, the computed relative risks and number of COVID-19 cases were merged into the Philippines provincial map, specifically a DESA map. Neighboring areas with dark colors indicate clustering because of the agglomeration of COVID-19 high-risk areas due to the nearness of the SIR values across the geographical area. For a spatial map, a clustering of high-risk areas can be observed in the NCR plus bubble, Benguet, where Baguio City is located, and nearby northern provinces. Another clustering can be observed in Davao and nearby provinces. I will now pass on the floor to Mr. Olvina.
Next up, Moran's eye and cluster maps. The value for Moran's eye is 0.391, indicating a positive spatial autocorrelation. It implies that the observations are not independent, with high values clustering adjacent to other high values and vice versa, since the p-value is lesser than 0.05. Visualized on screen are the cluster maps generated by the researchers, wherein a red shade represents high-risk areas, with blue representing low-risk areas. Hence, the researchers identified that the speculated epicenter of the COVID-19 pandemic in the Philippines, the NCR plus bubble, is plausible. Moreover, the northern provinces share another high-risk area clustering for COVID-19 in the Philippines.
Next, multiple linear regression model. Applying forward stepwise, the model on the screen is the MLRM model for COVID-19 SIR in 2021 with an adjusted R-square of 65.60%. The model below is an equivalent model. For MLRM results, there are 13 significant COVID-19 correlates at a 90% confidence level. But what could be the implications? A positive correlation for both licensed COVID-19 testing laboratories and healthcare workers may be because of the better tracking of COVID-19 in provinces or NCR cities with more testing sites. A positive correlation for bronchitis may indicate increased COVID-19 risk for bronchitis patients, but breast and cervical cancer patients could correlate to a rise in risk due to their weaker immune systems. Moreover, a negative correlation on pneumonia could be because regular pneumonia is less reported in today's time. Ever since COVID-19 pneumonia, which is classified under COVID-19 cases, became more prominent. Due to empirical observations for unemployment, higher COVID-19 risk corresponds to a higher number of unemployed individuals due to lockdowns during the pandemic. Males also show a positive correlation as affirmed in Boyer, while the results on seniors correspond with the fact that seniors tend to have comorbidities. On the right, a negative correlation for municipalities and barangays indicates that local government units do aid in mitigating COVID-19 transmission, while revenue collection is positively correlated with COVID-19. Moreover, results for birth of both sexes show that newborns usually stay at home, drinking colostrum to be protected from COVID-19. Lastly, results for wind speed correspond with Clausen et al. In that the risk of outdoor COVID-19 transmission is higher on days with low wind speeds, while a positive correlation on air quality index supports Capizzini's study that higher air pollution plays a role in higher COVID-19 risk. After checking and testing the assumptions, the residuals for the 2021 MLRM model were found to be independent and normally distributed with mean zero and constant variance. This ensures the model's validity. To elucidate, the TW value which was used to test for autocorrelation can be seen on the screen to reveal that the models exhibit no temporal autocorrelation, and errors are independent since the values are between 1.5 and 2.5. Furthermore, the significant predictors tolerance values also show no multicollinearity among the variables since the values range from 0.24 to 0.52, all of which are more than 0.10. Since the residuals must be tested for normality, the Shapiro-Wilk test was used. Both histograms resemble a normal curve. Additionally, with a p-value more than 0.05, we fail to reject the null hypothesis and thus the residuals are normally distributed. The normal QQ plot of residuals also affirms this by displaying points that form an approximate straight line, as seen on screen. Lastly, the MLRM assumes that the residuals have a constant variance. The residuals are homoscedastic, which can be graphically seen through the scatter plot. Furthermore, Levin's test also affirms that the residuals are homoscedastic since the values are greater than alpha, which is 0.05. So we fail to reject the null hypothesis and conclude that the residuals for both models have homogeneous variances. Shirl, please continue the discussion.
To our spatial model, based on the computed Moran's I, there exists significant spatial dependencies among NCR cities and provinces on COVID-19 risks. With this, the SAR model was applied to the data. As a result, there are 6 significant COVID-19 correlates at 10% level of significance, while there are 6 significant COVID-19 correlates at 5% level of significance. Compared to MLRM results, there are 3 factors that are only significant in SAR, namely hypertension, oral health, and hospital beds. The result for hypertension is in accordance with the World Health Organization and other studies that persons with high blood pressure have a higher risk of COVID-19 infections and complications, since this is the most commonly shared pre-existing condition among hospitalized COVID-19 patients. The result for oral health, which are individuals who receive basic oral health care, is significantly correlated to COVID-19 risks. This implies that better oral health leads to less risk of COVID-19 infection. The result for hospital beds supports the study of Kapitsini that fewer medical practitioners and hospital beds leads to increased fatality rates. This finding signifies the necessity of an effective healthcare system during a pandemic. A higher number of hospital beds for COVID-19 patients would aid in reducing COVID-19 risks. To continue, Mr. Miranda.
Shown on screen are the results when significant MLRM correlates were integrated into the SAR model, yielding 10 out of 13 significant factors. Wind speed is the only significant factor at a 5% level of significance, whereas there are 9 significant factors at 10% level of significance, namely unemployment, testing laboratories, bronchitis, number of municipalities, air quality index, senior citizens, revenue collection, pneumonia, and number of newborn babies. To continue, Ms. Ocampo.
To compare the predictive abilities of models, mean square error or MSE and mean absolute deviation or MAD was used. Among the 3, MLRM had the lowest MSE and MAD. However, due to the existing significant spatial dependencies among provinces and NCR cities, the SAR model is more appropriate with low MSE and low MAD. Additionally, MLRM SAR yielded the highest among the 3, being the least suitable for prediction. That is all for the results and discussion. Next to you, Mr. Miranda.
So, what are the takeaways of this research? Using MLRM and SAR, significant COVID-19 correlates were obtained. Results from the MLRM model show that the following predictors are significantly correlated with the natural logarithm of COVID-19 SIR at a 10% level of significance. On the other hand, on screen are the 12 significant correlates of COVID-19 according to the SAR analysis at a 5% and 10% level of significance. But when integrated with each other, the MLRM SAR model showed nearly the same correlates as the MLRM model, with only breast and cervical cancer, healthcare workers, and barangays being no longer significant. Finally, comparing the MSE and MAD of the MLRM SAR and MLRM SAR models, MLRM had the lowest values. Still, the researchers would nevertheless recommend the SAR model due to the existing significant spatial dependencies of COVID-19 risk in the Philippines. Ms. Ocampo, please continue.
For recommendations, future works can explore a more comprehensive formulation of the spatial weighting matrix that can further and correctly capture the spatial autocorrelation of the data. Moreover, time dependencies can be included, leading to spatio-temporal models. The following are our sources and references for this presentation. Again, our research is all about significant correlates of COVID-19 risk in the Philippines using spatial modeling and mapping. Thank you for listening, and I hope you all have a great day.